Hello students, this video is to help review for the first part of Unit 9. We were talking during Unit 9 about polygons, all sorts of different classifications of polygons and how to work with them. If you haven't already done so, please try to do the problem sets. For example, right now I'd like you to pause the video, try to do the Lesson 1 problem set, and then come back when you're done. These first few problems were a review of a formula that you know already. You already knew the sum of interior angles formula from a previous unit. It asks for a polygon of n sides. Well, if it doesn't give you n, you're going to use 180 n minus 2. This is the same exact expression, just switched around. We're allowed to use that. That's called the commutative property. An octagon has 8 sides, and the sum in degrees of these interior angles, we're using the same exact formula, the sum of interior angles formula. We know that n is 8 in this case, which means 1,080 degrees. That was choice 4, which I did not circle, but now I did. For question 3, the sum of degrees, same thing. We're doing the same formula, but in this case, it's a pentagon, which got 5 sides. N pentagon, really? Anyway, this should be 540 degrees. The fourth one, it's asking for the number of degrees in n interior angle, one interior angle of a regular pentagon. Of course, the word regular, that word regular means all of the angles are the same. All the angles are congruent, which means I'm going to find the sum of the interior angles, that's this part, and then I'm just going to divide by the number of angles, which is the same as the number of sides. I got 180 times 3, 5 minus 2. Then I'm going to divide that by 5. It gives me 108. For number 5, a fact that you should know is the sum of the exterior angles of any polygon is equal to 360 degrees. You should know that. It doesn't matter whether it's a 5-sided polygon or a 10-sided polygon or whatever the case may be. All the exterior angles sum to 360. Which means I need all of the exterior angles that I know, 68, 84, 60, and why didn't I use 140? 140 is an interior angle. So I used my supplementary angles to find that this exterior angle is 40, and then I add them all together. That gives me 252. X is going to be 108 because that's the difference between 252 and 360. For question number 6, it was a regular pentagon, which means each of the angles is going to be 108. That means this is 108. It also means that all of the sides are the same. It's regular, which means the sides are the same. That means this is an isosceles triangle. And of course, you know in an isosceles triangle, base angles are going to be congruent. So each interior angle, we figured that out here. Angle A is equal to 108. Then we used the triangle sum theorem. We knew that this angle and this angle were exactly the same. So we added them together with 108, gave us 180. Solved it to give us x equals 36. And again, getting real sloppy with circling these correct answers. Go to the next page of this. These were the short answer questions. Pause the video, try them out, and then see if you're right. All right, for this question, it asked for the measures of 5 interior angles. I'm sorry, it told us 5 interior angles, and it asked for the 6th. Well, we know that all of these angles that they gave us was 645. The missing angle is going to have to be part of 720, which is the sum of the interior angles of this particular polygon, which is a hexagon. So we did 720 minus 645, gave us 75. So remember to give a little summary statement. It might have helped you to draw a picture. It might not have. This is my artist's rendition of a hexagon. For number 8, it asked us to determine in degrees the measure of each interior angle of an octagon. That's 8 sides. Here's my picture. Each interior angle of any polygon is this formula, just like from before. So now we're going to be using 8 for our number of sides. We get 1080 divided by 8 is equal to 135, which means each interior angle of a regular octagon has a measure of 135 degrees. Now, the difference between these two problems, this says it's just a hexagon. All of the angles are going to be different. This says it's a regular octagon, which means all of the angles are going to be the same. So I feel comfortable with saying each of the angles is going to be equal. They're each going to be 135 degrees. Now, the next question asks for a decagon, and as you know, I'm very good at drawing decagons, so here is my own picture that I drew myself of a regular decagon. Each interior angle of a polygon, as we know, is 180 times n minus 2 divided by n. So I plug in 10 or substitute for both of these n's, and I get 144. So one of the interior angles of a decagon measures 144 degrees. Lesson 2 problem set. Please make sure that you start this by yourself and then come back to check your answers when you're done. In Lesson 2, we talked about rotating shapes, and you know the rotational symmetry formula is going to be 360 over n. In this case, we're asked for the rotational symmetry of a regular pentagon, 5-sided shape. So we did the minimum rotation angle, which is 72, and then every rotation of 72 degrees counts. So 72, this is 72 times 2, 72 times 3, 72 times 4. We never use 360 though, because any shape when rotated 360 degrees will carry onto itself. Another rotational symmetry question here for this one was a little backwards because it gave us the angle and asked us to find the number of sides. We know the angle is going to be 72, so we substitute that into the formula and solve for n. Over here we did a problem where it asked us to figure out which one has a rotation of 135 degrees. So I found the rotation angles of all of these shapes by dividing by the number of sides. 135 only appeared in the octagon list. A minimum angle of rotational symmetry is the same formula that we used before, 360 over n. Nonagon's got 9 sides, so I divided by 9. Here, the shape looked weird, looked like a cool star, but it just simplified to be a pentagon. It was a fairly regular shape with 5 sides there. We were looking for not rotating and making it overlap the original. So same thing as the previous problem number 2. We found all the angles of rotation and we identified the one that wasn't it. Incidentally, negative 72 means rotating it backwards 72, which is very similar to rotating it forwards by 288. Flopped, we talked about flopped when we talked about symmetry of shapes. Line symmetry is what you should be looking for. FL, that flopped, indicates a reflection, some kind of reflection. And if you draw any line through a circle, doesn't matter where you draw the line through the circle, as long as it goes through the center, it's going to flop onto its original shape. Whereas any of these other shapes, if you draw a line like horizontally through an equilateral triangle, it's not going to flop onto its original shape. For question number 7, it was a rotating continuously around a segment, and anytime you rotate a shape continuously around a segment, you're going to get a 3D shape. This 3D shape was a hemisphere. It's half of a sphere. And in this case, it tells us that it wants us to rotate around one of its sides. If you took this if you took this isosceles triangle and rotated it around its altitude, you would get this cone. But it's not asking about whether it's rotated about its altitude. It's asking about rotating it about one of its sides. So that must be this triangle. Last but not least, what's each angle of rotation that allows a hexagon to carry on to itself? We did 360 over 6. That gave us 60 degrees. And then each angle of rotation is 60. And then 60 times 2, 60 times 3, 60 times 4. As a hint, you never, ever, ever write 360. You can write that if you want points off. Any shape, when rotated to 360, is going to carry on to itself. Take a look at the second page of that second problem set. Pause the video, try it out, and then come back to see if you're right. Remember that when we talked about in class continuously rotating shapes, those 2D shapes would become 3D shapes. So if we took this and rotated around segment BC, it would become a cone. Anytime you rotate a right triangle around its side, it becomes a cone. Here is an example of something that you have to predict. We know that rectangles, and by extension squares, all are going to give you cylinders. A cylinder is what happens when you take any rectangle and rotate it about one of its sides, and a square is a type of rectangle. However, when you take a right triangle and you rotate it around one of its sides, as previously stated, it gives you a cone. It asks you to draw the shape and its rotation. The Regents is not going to ask you to draw the shape, but I am, because I want to see your art. For question 12, this was a question that stumped some students. It does look like a cylinder, except it doesn't have a smooth top. It comes up a little bit, like it has a little mountain at the top here, and then it has an indent because this part of it goes downward. So you can think of this as an inverted cone in the middle here. So if it's similar to a cylinder, if you wrote that, I was okay with that. For question number 13, it was a question that asked you to think about it a little bit. Minimum angle of rotational symmetry and measure of exterior angle formulas are exactly the same. So regardless of whether you're finding the minimum angle of rotational symmetry or the measure of an exterior angle of a polygon, of a regular polygon, they're always going to be the same. All right, moving on to lesson 3 problem set. There were a lot of proofs here. Pause the video, try to write the proofs, and come back to see if you did them right. Looks like we're back to triangle proofs, everybody's favorite subject. Take a look at these proofs, make sure that you're understanding what's going on here. We're using angle-angle-side postulate here. For the second one, we're using ASA postulate, angle-side, angle postulate because of the information that we were given. And then for this one, we're using SAS postulate and then CPCTC, remember that old gem. Incidentally, all of these proofs ask us to prove triangles that are congruent. We always, always, always should draw those triangles out. And in every one of these proofs, we're using as our reasons something about parallelograms, whether opposite sides are parallel, whether diagonals bisect. My advice to you would be to memorize all 5 of those parallelogram concepts, those parallelogram reasons, because you need to know, if it's a parallelogram, what 5 things you now know and are able to use in a proof. All right, take a look at the next page, 4, 5, and 6. These are more proofs. Pause the video, try them out, and then come back when you're done. All right, the fun continues with more proofs. Sas Postulate for this one. Again, we redrew both triangles. For this one, we used the SSS Postulate. We were able to use that very easily because the diagonals bisect each other, and we had a bunch of diagonals on this one. We also could have used SAS and vertical angles, but I chose to use SSS because why not? For question number 6, we redrew the triangles, and we saw that it was Sas Postulate. This one was a little tricky because we had to first prove that it was a parallelogram. Luckily, a parallelogram is any quadrilateral with 2 sides that are opposite, that are congruent, and that are parallel. So as long as we knew that, we knew it was a parallelogram. And then CPCTC, our old friend from the triangles unit. All right, moving on to lesson 4 problem set. Pause the video, try these out, and see if you got them right. This lesson was all about properties of parallelograms and using them to solve problems. You needed to know some of the properties of parallelograms to get this first one. We know that diagonals aren't necessarily congruent to each other. We also know that these alternate interior angles have to be congruent. I gave a couple of hints for number 3. It tells you what every parallelogram has versus what only these special parallelograms have. In this one, we just did a whole lesson about proofs on parallelograms, but if you draw a diagonal in a parallelogram, the 2 triangles you make should be congruent to each other. This was a mathematical problem, an algebraic question, which required you to use x for one of the angles, and the other angles just fell into place from there. We know that 75 is exceeded by 30 for 105, so 75 plus 105 is equal to 180. And again, consecutive angles are supplementary, so they add up to 180. In this case, we were told that there were diagonals, and we know that diagonals bisect each other, which means they create 2 congruent segments. And in this case, consecutive angles are supplementary, so we added this angle plus this angle equals 180, and then we back solved to find angle 2. All right, more solving parallelograms on the other side. Pause the video, try it out, and then see if you're right. As you can imagine, all of this was very basic problem solving using algebra. In this case, we were given some angles in a parallelogram, and we had to, well, first draw the parallelogram, because you probably couldn't have done this without drawing it, and then labeled it, and then see what the relationships were. These 2 angles were adjacent to each other, these 2 were adjacent to each other, but the 2 angles across from each other are going to be congruent. For question number 10, we were given 2 consecutive angles, which are supplementary. They add up to 180. So we solved and substituted that x back in. And then for number 11, we know that diagonals bisect. Many students had problems with this because it had a fraction in it, but just multiply by the denominator of the fraction, and you are good to go. Hang on, I did this question a little bit wrong. Oh no, wait, looks like it's right. This was a challenge question, and I will leave it to you to figure out what the answer was. Here's a hint. Use the slope formula. All right, moving on to the lesson 5 problem set. Pause the video, check it out, and see if you got it right. As you look through the answers, these correct answers here, please try to keep in mind that the easiest way to answer some of these questions is to just draw a diagram. If you draw a diagram or if you mark up the diagram that they give you, you should be able to get the right answer fairly quickly. All right, moving on to the next page here. Pause the video again, try to answer them by yourself, see if you got them right. Here's another example of the types of problems that you might see. They're algebraic problems that require you to know the properties of parallelograms. Consecutive angles being supplementary, for example. Diagonals bisecting each other. And special parallelograms like rectangles, you need to know that the angles that are created here are going to be congruent. All right, pause the video again, take a look at lesson 6 problem set, and see if you can get these correct answers. In doing these problem sets, you should have already seen that all we have to do is identify the properties of the different shapes. For example, in this case, it's trapezoids, and then apply them in different ways, looking at whether the mid-segment is drawn, looking at whether the altitude is drawn. All right, last but not least, this is the last page of the last problem set. Pause the video, try it out yourself. Here's the last page of the last problem set. Take a look at these correct answers. Hopefully this was helpful to you to review for unit number 9. All right, that's the end of the video. Good luck studying.